So students, welcome to the session again. So the last lecture what we did, we calculated a new variety of matrices which are simply denoted by the adjoint of a matrix. Actually, what is the purpose of calculating adjoint of a matrix? The purpose for calculating adjoint of a matrix is what? With the help of the adjoint of a matrix, we will calculate the inverse of a matrix, right? So in this session, we will discuss the concept of inverse of a matrix. So before proceeding the discussion properly, let me clear you one thing. Inverse, when we are talking about inverse, the matrix considered must be square. So throughout the inverse concept, the matrix or the matrices must be square. Means only square matrices may not have their inverses. We cannot talk about the inverse of a rectangular matrix, right? So before starting the formal definition of the inverse of a matrix, we should define two new matrices first. These matrices are known as singular and non-singular matrices. Singular and non-singular matrices, because these two matrices will play a very prominent role in finding out the inverse of a given matrix. So a matrix, of course, it must be square. A matrix A is said to be singular if A is a square matrix, condition 1. As I have stated in the very beginning, is a matrix A is said to be singular if A is a square matrix, condition 1, and condition 2, its determinant should be equals to 0, right? So what does it mean? If we want to know any matrix is singular, it must be square, and second, find out its determinant. If its determinant is equals to 0, then the matrix is said to be singular. It's a very simple process. For example, take the matrix this. A is equals to 2, 4 as a first row and 4, 8 as the second row. This, find out its determinant is coming out to be 16 minus 16, that is 0. Therefore, the matrix A is singular, right? The second case is what? Non-singular matrices. A matrix which is not singular is called non-singular. So a matrix A is said to be non-singular if, number 1, it is a square matrix, and number 2, its determinant should not equals to 0. So for a singular matrix, the determinant should be 0, and for non-singular matrices, determinant should be not equals to 0. So this is a matrix. If you find out its determinant is coming out to be 5, that is not equals to 0. Therefore, the given matrix is non-singular. So these two variety of the matrices will play a very prominent role in finding out the inverse of any given square matrix, right? So before proceeding the formal definition of the inverse of a matrix, you must think that why inverse is required. Actually, in the very beginning of the session of the matrices, I told you the matrices almost behave like numbers, but there are few fundamental operations or properties which are possessed by the matrix, by the numbers, but they are not possessed by the matrices. And among all those properties, the one property is division. In case of numbers, division is always possible. We can divide a number by any other number, but in case of matrices, the division is not possible. So what we should do? So the replacement of the division here in case of matrices is considered as the concept of inverse. For example, if I ask you, you have given an equation 2x is equals to 6, then what is the value of x? So x is equals to what? 6 divided by 2, that is 3. So this is an equation, we are dealing with the numbers. Therefore, what we did, we divide 6 by 2 to get the value of x as 3. But here, if you have an equation ax is equals to b, you cannot write down x is equals to b upon a, because a, x and b, they all are matrices. Clear? we cannot use the operation of division in case of matrices, and the substitute of the operation of division is considered as the concept of inverse. For example, see here, why inverse needed? If I ask you, how do I share 10 apples with 2 peoples? How do I share 10 apples with 2 peoples? So there are two ways. One, there are 10 apples, divide by 2, because they are being shared by 2 people. 2, this is 5. Each pupil will get 5, right? 5 apples will be received by one person, right? Because we can divide 10 by 2. The second option is what? See, 10 into, what is this? 0.5. This is equals to what? Again 5. So the result obtained here and the result obtained here is same. What is the difference? See, 10 upon 2, this can be written as 10 into 1 upon 2, and this is equals to what? 10 into 0.5, and 10 into 0.5 will be equals to 5. So the answer in both ways is coming out to be same, but the operation has been changed. Here 10 is being divided by 2, but here 10 is being multiplied by 0.5. So what is the difference between these two operations? 2 is a number, right? If I ask you what is the inverse of 2, so inverse of 2 is 1 upon 2. Clear? Inverse of 2 is 1 upon 2. Similarly, in case of matrices, we will use the concept of matrices to solve the various matrix equations, as we use the concept of division to solve the various equations in case of numbers, right? Clear? This is the basic idea between these two. This is simple division and this is by multiplying the inverse. 1 upon 2. What is 1 upon 2? 1 upon 2 is the inverse of 2, right? 1 upon 2 is the inverse of 2. So let us have the formal definition of the square of a matrix. A square matrix A of order n is said to be invertible if there exists another square matrix B of the same order such that AB is equals to BA is equals to IN, where IN is an identity matrix of order n, right? So what does it mean? It simply means if you have a matrix A, it should be square, okay, no doubt. To find out its inverse, what does it mean? We will have to find out another matrix that should be of square and of the same order, B, such that if these two matrices are multiplied, then the product of these two matrices should give you an identity matrix. Then B is called the inverse of A. Actually, both are inverses of each other. B is the inverse of A and A can be also taken as inverse of B. So the concept of the inverse is what? Say 2 is a number, and which 2 is a number. If we multiply 2 by 1 upon 2 and the product is coming out to be 1, right? So 1 upon 2 is called the inverse of 2. Then 2 is also the inverse of 1 upon 2, right? So the product of the number and its inverse is always equals to 1. Clear? In case of numbers. Likewise, the product of a matrix and its inverse, say example, it is denoted by A inverse. This is always equals to identity matrix, because the role of 1 in number system is very much similar to the role of an identity matrix in case of matrix theory or in case of matrices, right? So whenever two matrices of the same order are multiplied together and their product is coming out to be an identity matrix, then both are inverses of each other. This is the basic idea to define formally the inverse of a matrix. It should be noted that if the inverse of a square matrix is multiplied by the matrix itself, then the resulting matrix is an identity matrix, right? This is the formal definition. It may be noted that A inverse, the inverse of a matrix, is denoted by this, right? A inverse. It may be noted that A inverse doesn't mean 1 upon A. This is simply a notation to denote the inverse of a matrix. So, inverse of a matrix, if it is there or if it exists, every square matrix need not have its inverse, but if the inverse of a square matrix exists, it is being denoted by A inverse, right? Now, under what condition we can calculate the inverse of a square matrix? The condition is very clearly specified here. The necessary and sufficient condition for a square matrix A to possess an inverse is that it should be non-singular. Clear? I have told you these two matrices, singular and non-singular, will play a very important role in finding out the inverse of a matrix. So, necessary and sufficient condition means what? What does this statement refers to? If we have a square matrix, then it will have an inverse if it is non-singular. If it is not non-singular, means it is singular, it will not have an inverse, right? So, this is true in both way. Both way means if the inverse of a matrix exists, then it should be non-singular, one way. Second way, if the matrix is non-singular, then its inverse will exist. Clear? This statement is two-way. If a matrix is non-singular, its determinant should not equals to 0, means its inverse exists. And if inverse of a matrix exists, it means it should be non-singular. So, basic requirement for existence of the inverse of a matrix is only what? It must be non-singular, right? Now, expression for finding out the inverse of a matrix. So, we have seen in the last slides, A is multiplied with its adjoint. This is equals to what? If adjoint of A is multiplied with A, the product of these two matrices is determinant of A into I, right? Now, see, if the determinant of a matrix is not equals to 0, see, if the matrix is non-singular, only then this will be possible what I am going to write. If the matrix is singular, we cannot proceed. Clear? So, if determinant of A is not equals to 0, then what we can do? We can divide this equation by determinant of A both sides. So, what we will get? Say A into adjoint of A divided by determinant of A, right? This is equals to adjoint of A divided by determinant of A into A, and this is equals to what? This is I is left because we are dividing by determinant of A. Now, if we take this term as B, right? This term as B, so what we will get here? AB is equals to, this is B, I, and this is equals to BA, right? So, the product of two matrices is coming out to be an identity matrix. They are multiplied in which order, it is not important. AB and BA, in both way, the product is coming out to be an identity matrix. So, this B is called the inverse of the matrix A, and it is calculated by B is equals to adjoint of A divided by this. We can denote it by rather A inverse, right? So, the A inverse is calculated by this formula. Adjoint of A is divided by determinant of A, right? This is the formula to calculate the inverse of any square matrix. The next stage is what? Steps involved in finding the inverse of a matrix. What are the various steps required to find out the inverse of a matrix? The following steps should be taken to determine the inverse of a matrix. Step 1, find out the determinant of the matrix. Step 2, if determinant is equals to 0, we say that A is singular, inverse will not exist. The process should be stopped. If determinant of A is not equals to 0, Clear? If determinant of A is not equals to 0, it means the matrix is non-singular. Then we can proceed to find out its inverse. And we know what is the formula to calculate the inverse. A inverse is equals to what? Calculate the adjoint of the matrix first, and then calculate its determinant, and then divide the adjoint of a matrix by its determinant, simplify it. What else you will get? That will be treated as the inverse of a given matrix, right? And one thing more, whether the inverse you have calculated is correct or not. If A is a matrix and for example A inverse is the inverse which you have calculated, if this inverse is correct, you can use the definition A into A inverse must equals to identity matrix. So if your inverse is correct, then whenever the matrix A is multiplied with its inverse, the product of these two matrices should come out to be an identity matrix. Clear? Now let us take an example. I have taken here the matrix of order 2, and in a similar way you can extend the same concept of finding out the inverse of a matrix of order 3, right? So find the inverse of a matrix this. The first row contains 2, 5, the second row contains 3, minus 7. So see, this is the matrix A, right? Let us take, this is A, 2, 3, 5, minus 7, right? First step, write down its determinant, 2, 3, 5, minus 7. Right? I will explain every step so that you can understand it. First step is what? Write down this determinant. And what is the value of this determinant? Determinant minus 7 into 2 minus 14 and minus 15 into 3 minus 15. This is equals to minus 29. So this is not equals to 0, right? We came up to here. This is not equals to 0. It means the matrix is non-singular. Therefore, its inverse will exist, right? So inverse will exist. And what is the formula to calculate the inverse? The adjoint of A must be divided by the determinant of A. Determinant of A we have calculated. Now find out the adjoint of the matrix A. We have calculated the adjoint by using the formula. This is the first cofactor, this is the second cofactor, this is the third cofactor, this is the fourth cofactor. Right? Then the adjoint of A is finally minus 7, minus 3, minus 5, minus 2. This is the adjoint. Right? Now, by our formula, what I have discussed, see, this is the matrix. These first diagonal elements should be reverted. So, what you will get here? You will get here, this is minus 7 and this is 2. And they should be multiplied by minus 3, minus 5. See, this matrix and this both are same. Anyway, you can use any one of these two techniques to calculate the adjoint. See, once the adjoint of a matrix is calculated, then we can use A inverse is equals to, see, adjoint of A divided by determinant of A. Now, what is the value of the determinant? Minus 1 upon 29, and adjoint of A is this matrix minus 7, minus 3, minus 5 and 2. So, what is A inverse? A inverse is simply multiply 1 upon 29 within this matrix, you will get the same result. That is 7 upon 29, 5 upon 29, 3 upon 29 and minus 2 upon 29. This is the inverse of the matrix A. And what I told you, we can also check our calculation. See, we have checked it here. If A is correct, then A, if multiplied with its inverse, the product should come out to be an identity matrix. This is the matrix A, this is the inverse. Multiply these two matrices and the product of these two matrices is coming out to be an identity matrix. So this is how we can calculate the inverse of any matrix. So simple procedure is what? To find out the inverse of any matrix, first write down its determinant. If determinant of the matrix is not equals to 0, it shows that the matrix is non-singular. Then we will proceed to find out the inverse. So what is the next step? We will calculate all the cofactors and then find out the adjoint of a matrix. Once the adjoint of a matrix is calculated, to find out A inverse, adjoint of the matrix A should be divided by determinant of A and then simplify it. What else you will get, that will be considered as the inverse of a given matrix, right? Find the inverse of a matrix. So this I will leave for you and as an exercise, because we will use the same approach as we used in the last case, that is the matrix of order 2, and the difference is what? This is the only matrix of order 3. The step is what? Write down its determinant. This is the determinant. Simplify it. The determinant is coming out to be -5. It means the matrix is non-single. Therefore, its inverse will exist. Now, we will find out the cofactors of all the 9 elements of the determinants as A11, A12, A13, A21, A22, A23, A31, A32, A33. Then find out its adjoint. And finally, divide the adjoint by its determinant, you will get its inverse. The approach is completely verbatim to find out its inverse. So, try to find out its inverse yourself for the sake of practice, right? See this case, verify 1 upon 6 of this matrix is the inverse of the matrix this. See, this exercise is completely based on the formal definition of a matrix. What you want to show? You have been asked, show that this matrix is the inverse of this, right? If A is a matrix, then B is called its inverse if AB is equals to identity. This is the definition of the inverse of a matrix. So what we should do? How we can verify that the first matrix this is the inverse of the second matrix? Just think over it. By definition of the inverse of a matrix, if the two matrices are multiplied, then both are called inverses of each other. So if the first matrix will be considered as an inverse of the second matrix if both of these two matrices are multiplied and the product of these two matrices is coming out to be an identity matrix, the formal and basic definition of the inverse of a matrix. So multiply these two. If the product of these two matrices is coming out to be an identity matrix, then it will show that the first matrix given in the question will be the inverse of the second matrix. What we did here, we did the same thing. This is the matrix A, we take this as a matrix P. So what we did, A into B. See, we multiply A into B. And the product of these two matrices, you can multiply these two matrices. I have already explained the procedure for multiplication of two matrices. Multiply these two matrices, the product of these two is coming out to be an identity matrix. If the order is reversed, like BA, the definition is what? AB is equals to I and this must also equals to BA, because A and B both are considered as inverse of each other. So we will calculate BA also. When we calculate BA in the same way by multiplying these two matrices, then the product of BA is also coming out to be an identity matrix. So AB is equals to BA is equals to I. It shows that the first matrix, this 1 upon 6 times of this is the inverse of this matrix. Clear? This is how we can show that a matrix is the inverse of the other. Now, before proceeding some more examples, let us have some properties of the inverse of the matrix. Actually, properties of any new concept, whatever we are discussing, is very important. The reason, as I have told you many times earlier, sometimes properties help us a lot to find out the solutions of few questions in a very simple way, right? In other way, we can also say that to avoid a kind of complications in the calculations, we can also use the properties in some cases to find out the solutions of the various questions. So as far as the properties of the matrix inverse are concerned, we have discussed only few properties. Property 1 is what? The inverse of a square matrix, if it exists, is unique. Unique means, I have told you in the first lecture of the function, unique means only one, right? Unique means only one. So the inverse of a matrix may not exist, right? If it exists, it will be only one. This is the meaning of property 1. We cannot have two different inverses for a single matrix. Clear? We cannot have two different inverses for a single matrix. This is property 1. Property 2 is what? If A is a square matrix, then A inverse and A inverse exist, then A inverse of inverse is equals to A. This is a very much similar property to the transpose what we did. If A is a matrix and AT is its transpose, if you take the transpose of a transpose itself, the matrix we will get. Similarly, if A is a matrix and A inverse is its inverse, if you take again the inverse of this inverse, you will get the matrix itself. This is property 2. Second thing, inverse of the transpose is equals to A inverse of transpose. Right? You can verify these two properties yourself. Case 3 is what? If A and B are invertible matrices of order n, then show that AB is invertible and AB inverse is equals to B inverse A inverse. Now this is known as the reversal law. If we have any two matrices AB and we multiply AB, so the product of AB, if we take its inverse, this is equals to B inverse and A inverse. So keep this formula in mind. It is not equals to A inverse, B inverse. Be careful, right? This is known as reversal law. Property 4 is what? Let A, B and C are three square matrices of order n such that AB is equals to AC. If A is non-singular, then B is equals to C. What does it mean? If A, B, C, they are the three matrices. This property we have already discussed in case of matrices. If A, B, C are three matrices and the product AB is equals to, for example, AC, then B is equals to C, then B will be equals to C if determinant of A is not equals to 0, right? If AB is equals to AC, then B and C will be also equal if determinant of A is not equals to 0. But if determinant of A is equals to 0, then BAB is equals to AC. It does not imply that B is always equals to C. And if you recall the last lectures, I have given you the example of this case. If A, B, C are any three matrices and AB is equals to AC, then it is not essential, it is not mandatory that B is equals to C. B and C may be different matrices, clear? But if AB is equals to AC, then B is equals to C. B and C will be same if the matrix A is non-singular, means its determinant is not equals to 0, right? The last property is what? If A is a non-singular matrix, then A inverse is equals to determinant of A, means if A is a matrix, then all these things, if you take the determinant of the inverse, this is equals to determinant of inverse of the determinant, right? So what does it mean? It means, see, from here we can write it A inverse determinant, this is equals to 1 upon determinant of A, right? So these are the few properties which I have taken into consideration, and be careful and try to keep all these properties in your mind, because we will use any property in any particular situation to find out the solution of any problem, right? So students, we should stop it here. Thank you very much.